I'm here to deliver a talk on comparing Java startup options with Quarkus. And we've got quite a few options to get through, so I'm going to get started, and hopefully we can get there by the end of the session. Let me just get set here. There we go. My lawyers well, not mine, IBM's lawyers like me to put these up in my talks, so you can read that later at your leisure. If you haven't met me and or seen a keynote this morning where I was speaking, my name's Mark Stoodley. I'm a senior technical staff member and chief architect for Java at IBM. So I get exposed to all of the Java products that IBM writes. There's roughly 250 of them that build on top of the Java that my team builds. So we build JVMs and put them into JDKs and ship them and make them available for use by IBM products. So I have a little bit of experience working with Java. My background's mostly actually in computer architecture and compiler optimizations. So I actually write quite a bit of C++ code, but I have written a few lines of Java before. And I'm here to talk about what kinds of startup options you have in your choice of JDK and JVM to help you run Java applications faster. And we're going to look through the lens of Quarkus on how those options actually work. So the outline for the talk is I'm going to start a little bit talking first about what does it mean to start Java applications fast, and how do we categorize fast, and how do we measure fast. I'm then going to give what I'll call a whirlwind overview of JVM technologies. I've basically got one slide per technology that we're going to look at, and I think there are 6 or 7 of them. So that we're going to work our way through those. And then as part of that, I'm going to give an actual kind of a scorecard, traffic light sort of notion of each of the technologies and look at it from a variety of different perspectives. The third bullet is a mistake that shouldn't be in the deck because we don't have time actually to go through the measurements. We did look at measurements in my workshop on Monday where we talked about this stuff, and my workshop will become available as a GitHub repo later, but it's not actually part of this talk, so I apologize. The third bullet is not something we'll be doing today, but I may wrap up at the end. All right, so let's get into startup. So I've made yet another, I think this is the third of these diagrams that I've written for this conference. Somehow I keep coming up with different ways of doing this. Looking at sort of the life cycle, the general life cycle of a Java transaction-based server. So at the beginning, we'll call this the beginning for now, which is just somebody wrote Java or a script issued a Java command, and it takes some time for Java to get started and to the point where the JVM is actually up and running. Then from the point the JVM starts running, it has to run the main class of the program and your application framework, like if you're running Quarkus or if you're running Spring Boot or if you're running WebSphere Liberty, there's this time that it takes to initialize it. From that point forward, then there's probably an application loaded into the framework that needs to be initialized and run, and so that takes time. And eventually, at some point, enough stuff gets loaded and enough stuff gets compiled and enough data is present that we can actually start processing transactions that are being applied as load to this server. And we start off at almost 0, like 1. And then over time, we have to compile code, we have to load classes, we have to initialize data structures, fill in caches, etc. And so the performance of the server ramps up through this period until eventually all of those things are kind of settled. Our caches are all full, our data structures are all loaded up. We've compiled the JIT has compiled all the code that we need, all the classes are loaded, and we sort of reach this kind of steady state kind of period. Now obviously this is very abstract. The real diagrams are much more noisy but for this discussion we'll just keep it at this level. Now if I'm firing up this server in order to process requests, and that means that there's people trying to send requests to the server, at the very beginning of this whole section, until I actually get to this point of being able to respond to the first request, the server is as if it's not there, right? So this whole time period of startup is the time that you're not responding to transactions, you're not responding to what it is that your server is supposed to do. So your business isn't making money, or it's not doing what it's supposed to be doing in order to satisfy its requirements. So this startup time is actually pretty important. Now, if you look at the time that a framework will tell you, like for example, Quarkus has a message that it prints out once it's started itself up. It says powered by Quarkus, version. Yes, that's a slightly old version, don't worry. Started in 2.507 seconds, so it started in that time period. What it's actually measuring is the first moment in time when it could get the time from Java, which means the JVM's already started and a lot of stuff has already happened, until it can actually take a timestamp of it thinking itself has been started up. So it's not really all of this whole period. Now, remember, this isn't to scale, so this probably is the biggest part of it, but nonetheless, it's not the full time period. If you talk to JVM guys like me, we like to focus on the startup of the JVM itself, which is pretty short, right? I just ran it once in a container on a VM in our infrastructure, and it was like 70 milliseconds to get started, right? So that's 70 milliseconds on top of that 2.5-ish stuff, plus probably there's a little slop in here. So ideally, we'd want to actually measure that whole time period just to make sure that we're capturing the full startup of the thing. But that's still not the full time that our server's not doing anything. So it's actually better to measure time to first response. But that's a little bit harder to read because how do you know when the first, the server itself doesn't really give you a good idea of when the first response has been received, right? It knows when it processed the first response, but it doesn't know when the receiver got it. So in order to measure that, we have to be outside the JVM. And then that brings another question to mind. So if I'm running this in a container, I really need to wait for the container to get started up, right? So at the very beginning of this whole process, somebody ran podman run or docker run. The container took time to get started. Then once the container got started, it took time to get to the point where a Java command could get issued. And then the whole process that we talked about before comes along, and all of a sudden we're measuring. So I don't talk about it very much in this talk, but in the systems that I was measuring in my workshop, this time period is somewhere around 500 to 600 milliseconds. Yes, it's an older machine. Some machines will be different. That was actually 500 to 600 if it's pinned to a core. If it's not pinned to a core, it could be anywhere up to a second or 1.2 seconds even. So this time period actually is not insignificant, and it really should be something you measure, because in a real production system, if you're starting containers, you are paying this time. So if you're comparing the options of how long this is taking and you're ignoring this, then you're really not making the right choice. You may not be making the right choices. So just to highlight that, just to make an extreme example, let's say I gave you two Java startup options. One starts in 1 millisecond, and the other starts in 10 milliseconds. Which one will you choose? Probably, given all other things are equal, 1 millisecond, right? I'll start in 1 millisecond. Why wouldn't I start in 1 millisecond? What if I told you that those times only start 100 seconds after you actually start? So I can start in 100 seconds with 1 millisecond, or 100 seconds or 101 second, or 100 seconds plus 10 milliseconds. And not all your applications would work if you started in 100 seconds with 1 millisecond. So now the trade-off is very different, right? It's only a little change on the end. So in computer architecture, we call this Andal's law. Your improvement is actually limited by the part that you're not speeding up. So for all that we're going to be talking today about how you speed up, how Java does all this stuff, you can't ignore this chunk here. And it should be factored into any decisions that you're making around technology choices around your Java application deployments. Okay, so that's time to first response, but that's not the only thing we should care about, right? Oh, actually, sorry, let me talk about that first. How you can measure first response. So you really, in order to do it from outside, you need the container to get up, and you need to find out what its IP address, and then you need to be able to send a response to that IP address and validate the response. So I just put a couple of quick things here. I don't expect you to absorb this in the talk while you're sitting there, but there's a way of getting podman inspect to get the IP address of any particular server or container that you're looking at. That once you have that IP address, then you can use a curl command to just kind of ping it at some endpoint. In the applications that or the microservices that I was doing in my workshop, each of the microservices has a status endpoint that you can ping, and when the status endpoint finally responds, you can say that's when the first response comes back. And so you should be measuring time for first response from outside the container. Don't believe anything inside the container. You should be pinging it from outside, because that's what the transactions in your real world scenario are going to be doing. All right. But first response isn't the only thing we should care about. We should probably also care about throughput, right? Like how much performance are you actually getting? How much time it takes to ramp up, right? The longer it takes to ramp up, probably the worse, right? You'd like it to ramp up very quickly, so you're getting high performance very quickly. And it's also important to know how much memory is being consumed, because especially if we're deploying these things into cloud resources, the things that cost money are cores and cores, so how much performance you're able to you need to deliver your to handle your workloads, and memory. How much memory do you need to process your workloads? And so the more memory translates into more resources, and which means more cost. So and at some level, that even matters if you're running on-prem and not in the cloud, because you still need machines to run stuff, and you still need to pay for memory to run workloads, etc. So there's a few things here. In a lot of blog articles, especially the ones from frameworks, you'll see them measure this point. You'll see that how much footprint is being used, what's the resident set size once you hit the first response. And that's an interesting number, especially if you're a framework person who wants to not have to worry about what the application's doing. But it's not a very useful number, because it's typically very different than the number that you would measure at this point, where you're actually hitting steady state performance. Because at this point, you haven't actually done very much, so you haven't loaded very many objects because you haven't handled very many transactions. If you're actually at steady state and you're handling 100 or 1,000 or more times the transactions per second, you need a lot more objects, you need a lot more memory, and therefore you need to know what the memory needs are going to be at this point. And then on top of that, you might actually also be interested in what the peak memory usage is here, because obviously you can't just start a container when you reach steady state. You have to allocate the container right back here, and it has to have enough size to deal with whatever your peak memory usage is. And depending on what you're doing, a lot of JIT compiles might be happening in these early stages, which are driving memory up very high, and you need to make sure that you allocate enough size in your container in order to take care of all of that work. So I'm going to only look at a few of these in this presentation. In my workshop on Monday, I actually kept pretty much all of them around, which made for a nice big table of numbers, but which I'm not going to show today. But I'm going to just simplify the considerations a little bit for this talk, just so that we don't have to go through too many different things. Now, how do you measure memory? Basically, you need to measure the resident set size. So that's the amount of memory that's actually being used physically in the machine in order to run the workload, which is very different, or can be very different, than the amount of virtual memory that's being allocated to the machine, to the process. So virtual memory is like JVMs tend to reserve a lot of memory and virtual memory address space, but it doesn't actually consume physical resources unless it needs it. So you don't want to look at virtual address space. You definitely want to look at resident set size. And the thing that you need to measure it is you kind of need to know what the PID is for the Java process that's inside the container. It's possible to read it inside the container and pop stuff up, but it's kind of nicer in a way to be able to get it from outside. There are also obviously metrics and telemetry ways of achieving this. This is a very low-level way, and I trust it because it's actually Linux telling me how much memory is being used. Many of the other ways are some number of arm's lengths away from what the actual operating system is managing and providing. So this technique, I know, is quite accurate for figuring out what the resident set size is. You should make sure before you use another metric that it actually tracks well with what this number is, or else you may be deceiving yourself about what memory consumption is really there. So the idea here is, so you have to identify a process for a Java process, but if you have multiple containers running on the same system, it might be hard to identify them. One trick that I've used, and I used in the workshop, was basically to invent a system property that appears on the Java command line that lets me identify for sure which service I'm talking about. So in the case of my Acme Air flight reservation system that I did on Monday, there was a booking service, an auth service, an authentication service, a customer service, a flight service, and so they all had these things on here. There's probably some other class name or some other thing that you could probably use to identify it as well, but you can always just tag it with this thing and then be sure. And then finally, if you want to get the PIDs that have that booking service, you can obviously use PS to do that, with a lot of ways of stripping out the grep, using grep to find it, and then getting rid of the grep that has this name in it already, and then printing out the actual memory. And you can look at the S maps. If you're on Linux, you can look at the S map for the PID and pull out the RSS numbers and total them all up. So there's a lot of gobbledygook there. You can go and look at the slides afterwards. I'll make them available. Don't bother trying to write it down, or you can take a snapshot if you want. But you can also use PS-O RSS and PID. But if you read online, sometimes you might get slightly not the right answer from this, so it's always best to look directly in the S-maps, because that's actually reflecting the current state of the residence that's at that moment in time. All right, and then another metric that I'll tack in here is kind of like you have to get this thing together in the first place too, and so a bunch of the options have some different impacts in terms of how long it takes you to build the container that you need to do this. So obviously in your deployment step, it's not necessarily like you build it, then you run it. Every time. You probably build it once and then run, but eventually you have to build it again, and in your CI system, the time it takes to build is going to factor into the productivity of your team, and how often you can afford to run tests, how many resources you need to run tests, etc. So I'll also tack that one in, and we'll just talk about what the implications are on the, or what the different JVM technologies do in terms of build time. All right. But there are lots of other ones. Obviously, there's you could measure the size of the the container that you create. You could measure the size of the topmost layer in the container that you create. You could do the time to fetch. If you're concerned about cold starts, you could measure the time it takes to fetch the container from a remote registry to the local daemon on a system. If you're running with Kubernetes, you might be interested in the time it takes to start a pod or to start a node. Those are both much longer than the time it takes to start a container. So again, going back to Amdahl's law, if you're making choices among Java startup options, and you're adding all of these other overheads that you're not actually improving, then that changes the trade-offs that you might want to apply. So the one point that I'm going to make here is that you can't use a technology that improves startup. You can't use it in isolation. You have to consider the effect on other metrics at the same time, and that's why I've gone through all these different metrics, and we'll start to look at this a little bit more closely. But once you bring multiple metrics into it, you're going to have to decide how much you care. So please, nobody just walk out after I say this. But you're going to have to figure out for yourselves how important is time to first response, how important is throughput, how important is peak memory use. And that might be different for different applications, from one application to another application because of the way it gets used. It might even be different between different deployments of the same application because they get used in different scenarios or for different sets of users or for different purposes. So these are questions that you need to answer and you need to take to heart if you really want to make a logical, well-reasoned decision about what to use. And finally, my recommendation is don't trust verbatim any blog or presentation to do it for you, because they don't know your preferences. Your preferences depend on you, the systems that you're building, that you're deploying, and that ultimately you're next on the line for. The blog author isn't going to help you, and that includes this presentation. Obviously, I took this slide from the workshop. But I'm going to try not to tell you what to do. I'm trying to give you the tools and information so that you can make well-reasoned decisions yourself. That's what I'm trying to achieve here. Okay, so here are 6, I guess was the number, 6 different technology options that you can use just by swapping out your JDK or by setting some command line options in order to impact how fast your Java applications will start without having to necessarily change your Java application at all, right? So all of these are just basic deployment options, and your application doesn't have to do anything in principle to take advantage of these. Although you do have to learn which command line options are there, learn to use them properly. You may have to add additional steps into your CI or into your running environment in order to take advantage of them. So let's quickly go through them. So class sharing is basically just targeting that cost of class loading. As we all know, Java loads its classes dynamically. In typical microservices can have thousands to tens of thousands of classes that have to be loaded. That's a lot of work, and so if we can reduce that work, then we can improve the startup time of the Java application, and it's just the JVM that has to do that. AOT class linking is a relatively new form of this, which was released in JDK 24 in the hotspot JDK, which takes it a little bit further and tries to do a little bit better job than so a hotspot's app CDS, for example, and it's a work in progress. It's not done yet. They're still improving it, but we're still going to talk about it a little bit here. I should have mentioned for class sharing, there's Hotspot's app CDS, which is application class data sharing, and OpenJ9 has a thing called the shared classes cache, which we'll talk about in more detail in the next few slides. The third thing you can do is cache JIT code, right? So we all know that JVMs use a JIT compiler to compile the code that you're running at runtime, and they do it every time you run your Java application. So if you call println, println's getting system out println, that gets compiled in every single Java run that you do, and it's probably not very different in each run. So why are we wasting all that time to compile and recompile and recompile and recompile? We could just save it in a cache and reuse it, right? So OpenJ9 is shared class cache can actually store cached JIT code, which we confusingly call dynamic AOT, just for fun. And it helps with that, not having to do so much JIT compilation. Checkpoint restore is probably most famous under the OpenJDK crack, coordinated restore after checkpoint project that's at OpenJDK. This one's available in several JDK distributions, and basically it tries to just start a Java application to a particular point in time, and then snapshot it, store it to disk, and then bring it back, and you can run from the restored state. So it's very fast. It can bring an application up very quickly. But it does have some potential impacts for applications and how they get used, so we'll talk a little bit more about that. Remote JIT compilation basically takes the JIT compiler that's inside the JVM and moves it to a separate service so that all of the resource requirements of the JIT are somewhere else, and you can independently deploy them and figure out how much resource you want to give them, and the resulting JVM process no longer has a JIT in it, so it behaves very regularly and more or less according to what the application is doing inside it, and not this arbitrary JIT compiler thing that nobody understands. Semru Runtimes has its Semru Cloud Compiler. Azul, as part of their paid offering, Prime, have a cloud native compiler as well, which can do this kind of thing. And then finally, native images, which probably everyone has heard about, where you basically say, all right, what if we didn't allow dynamic class loading, and we assume that we know everything, every class that's in this application, we'll just compile it, we'll throw compiler technology at it, and we'll build the code ahead of time, collapse as much down as we can, and we'll create a single executable. And so, so we'll also consider that one with Graal VM Community Edition. And this is now, there we go. All right. So I'm going to start off with just the pure Java things, because pure Java things are probably what you're using already, right? This is just running a Java command with an existing JDK. So Hotspot and OpenJ9 are the two basic options here. And so I'm going to use this, I guess, 6-column way of considering things. So we're going to look at usability, how easy it is relative to just running a Java command. Obviously, these two options are just run a Java command, so it's the same. So we'll call that green. But we're going to say, I'm going to argue, although I haven't really demonstrated it yet, I'm going to say that they're kind of the worst options in terms of time to first response and time to ramp up. And that's basically because you're doing all the work at runtime, every run, and you don't have any way of kind of reusing that work or saving that work by reusing it. Peak performance, however, is very good. For Hotspot, I'll give it a full green. For OpenJ9, for a lot of things, it's within 5 to 10%. For some things, it's actually better than Hotspot. I mean, it's like anything, right? You've got two options. Sometimes you're better. Sometimes you're not as good. Sometimes you're about the same. I would say most of the time for microservices and large applications, we're about the same, within 5 to 10%. If for some things, we're just a lot better, just because we've accelerated something that Hotspot hasn't, or etc. So there's variation here, but I'll give Hotspot the win. Steady state memory use. OpenJ9 is well known for its low memory consumption under load, so it uses about half the memory of what you would normally use with what you normally see with Hotspot. So I'm going to give, these are all relative, of course, but I'll give OpenJ9 the green, and I'll call Hotspot red because it is traditionally using more memory. And then finally, for peak memory, Hotspot's going to stay red, even though it's usually just about the same as its steady state, but it was already red, so I felt bad not keeping it red. And then I downgraded OpenJ9 because OpenJ9's JIT compiler often causes spikes in memory, which cause quite high peak memory use. So we're going to call that it got worse its peak memory use is worse than its steady state memory use. And that could be like a couple of hundreds of megabytes of memory that we're talking about. All right, so let's very quickly, how am I doing for time? Ooh. All right, this really is going to be a whirlwind here. So I'm not going to spend too much focusing on each of them because I kind of explained all of them a little bit already. So in the app CDS class sharing model with Hotspot, you have a Java application which through some process called a training run, you basically run the application once, you collect a bunch of data from it, and it figures out from that how to build what's called a shared archive. That shared archive can then be loaded into any future run of that program, and it will basically load the classes that you're sharing from the shared archive instead of from all these jar files that the original run got it from, right? So you can still use other jar files. You don't have to necessarily have all of these jar files around, but you do need this shared archive, and it can be loaded into different applications, and it'll reuse what it can. Quarkus actually makes it really easy to package this guy, because if just by defining this little property here on your Maven package line, it will manage the training run for you. Very easy. So you don't even have to do the training run yourself. It will just go through and do a training run. It will try to manage how that execution works so that it doesn't have to do anything that would tie it to your production workloads. But it will generate this shared archive in a specific place, so you have to then tell it where to find the shared archive, but that's all very regulated. You add some extra command lines like this to your running Java command line, and that just tells it where to find the file that got generated that happened. One downside of this one is that if you turn on ASLR, so address space layout randomization in Linux, which is unfortunately a good security policy to do, it means that the shared archive may not work because it requires being loaded at the same address. And so if the address space is being randomized, you don't get the same address, and so you might not be able to use it. Doesn't mean your Java command will fail, although you can make it fail, but it does mean that you won't get the benefits of having a shared archive. So if I add this one into my list, so I'm going to insert all the hotspot ones at the top here, so I'll just go across here. So you have to do a training run, although Quarkus makes this very easy, so I'm a little bit loath to make this an orange, but I had to point out that the training run is there. This only works on classes, so it does improve on the time to first response, and it does provide some benefit to startup, but it's not as much as some of the other options that we're going to go through. And it doesn't really help with ramp up a little bit. Maybe I should have made these both kind of pink, because there are classes being loaded during ramp up, so that does help with accelerating that a little bit too. Peak performance doesn't change, and neither do the memory consumptions change. At least I didn't measure it when I was seeing it when I was doing runs for the workshop. Okay, next is AOT class linking, which is only available on Hotspot for JDK 24+, so that's the most recent JDK release that just came out. That's not an LTS release, but it'll be there in 25 when it comes out in September. And you'll see the picture is almost the same, almost identical, and that's because Quarkus also provides a very simplistic way. You just add, on top of the one that we just did before, you add this Quarkus jar app CDS use AOT equals true, and almost reads itself, right? Instead of generating an app CDS archive, it will generate an app.aot archive, which is the class AOT class linked. And basically, so class linking is more of the class loading process as being allowed to be persisted in this file, so that it doesn't have to, the JVM doesn't have to do as much work to load classes into the running JVM when it starts up. And that's a slightly different option that you have to select. There's no space there. And again, it will if it can't load it, it will still run, but you can make it break. Like you can make it stop if you want to, if you want to discover problems with your our archive building, etc. And otherwise, it's exactly the same as the previous slide. The other thing is that AOT class linking can survive ASLR, so it is a definitely better approach for loading classes dynamically, but it is very new, and it currently only works with system class loaders and not with user class loaders, so that can limit the number of classes that it actually can apply to, and that's what ended up causing problems in my workshop, is because Quarkus applications, or at least the application that I was running, was loading substantial number of classes from user class loaders, and that's not uncommon. And so, I'm sure this will get better, but for now, it's limited by the fact that it's only applicable to system class loaders. So if we go back to the scorecard, again, there's a training run. Again, it's only system classes here, so I made this a slightly darker pink. The traffic light system kind of broke down because I had to get so many variations in color. And again, the last three don't really change with this one, so you still get the same peak performance, but you still also have the same memory performance. It's not doing anything for your memory consumption, at least that I could measure in the tests that I was doing. Now, I didn't run multiple JVMs at the same time, so maybe there would be some benefit if you did that. All right, Eclipse OpenJ9's shared classes is kind of similar. It's trying to do the same kind of a thing, but it operates in a slightly different way. So with shared classes, you just put a -x share classes, and you can, specify the name of the cache that you want to use, and the cache dir. There's all kinds of options you can put on here. But basically, you just add that command line option to every run of your program. And then whatever the first run is will create this shared class cache. And as classes are being loaded by this thing, it will get written out. In the hotspot approach, this file, or whatever the shared archive, gets written basically at the end of the run, after everything's been done. In the shared cache run, it's storing classes instantaneously into this shared class cache and building it up as on the fly. And then you can connect multiple applications to the same shared class cache. You can even connect them while this one is building it, etc. It's a very flexible approach. Generating on the fly during all runs. Quarkus doesn't integrate support for this, so you have to do this run yourself. And in fact, if you're working in containers, because of the way containers work, you really want to do this first run in the build step of like while you're building the container. Because if you do it in the run step of the container, you'll spend a bunch of effort building this cache, and then when the container goes away, so will the cache that you just built. And the next time you run the container, you'll have to do this run again. And in fact, we adjust the heuristics a lot so that this actually does, it will not start as fast to build this cache as it will to run out of this cache, or even by default to run the program, because we're doing things slightly differently. So you'll get a slow application run every time if you just do this in the Docker container itself. So you want to build it, run the application once inside your container, as much of the application as you want inside the build step, so that it generates this as part of the container, and then you can just ship that across to whatever machine you want, and those runs will run out of the container, the shared class cache that's in the container. Another difference with this is the shared class cache, which isn't really a cache, can contain classes, JIT compiled code, as I mentioned, the reused JIT compiles, profile data, JIT hints, and GC hints. So a whole bunch of stuff that helps make the JVM run better based on what it learned from this application, or even sometimes these applications as they run. So if we add this one into our talk, I'm going to say there's no benefit in the first run, but then you get great benefits in the next run. So I didn't want to quite give it a full green, but it's a pretty good green. So we're really getting into shades of colors now. And I'll say time to first response, I'll get down to orange or yellow, whatever, because we are storing classes and JIT code for system and user class loaders, so we get access to everything, and we do make measured improvements in time to first response and time to ramp up. Time to first response is usually sped up by on the order of 30% with OpenJ9 if you have a properly configured shared classes cache that's built in the build step of the container and then runs afterwards. And again, that's with no impact to what your program's doing. Same thing with peak performance impact peak performance and steady state memory and JIT compiler. So we're not doing anything basically here with to improve these things. Checkpoint restore. What are we doing for time? Getting there. Checkpoint restore with OpenJ9 using crack, so coordinated restore after checkpoint. So OpenJ9 supports the crack API right now. Supports is a little bit strong. We're working on support for the crack API. It's available in our builds. You can use it when they run. Our Docker containers include the CRIU that's needed in order to run this, so it all works. But we are still trying to kind of roll out the support for it to frameworks and other things so that you get a more seamless user experience out of it. CRIU basically just takes a snapshot using a camera, no it doesn't use a camera, of this application, stores it to disk, so you have this checkpoint that's written on disk, and then you can ship that that snapshot along, and then you don't have to do all of the work that happened before the checkpoint. That just get magically, and then you start running from that point forward. That's what I was trying to depict there. Don't know if that quite came across, but you can do a checkpoint on one system and move it to another system, but there's some complexity involved in that because when you take a checkpoint of a running system, you may have allocated resources that know things about your build environment that may not be true of your production environment. And so if you're not careful, you can carry information from your build environment to your production environment that may not be appropriate. Like, for example, you might build on a system with 16 cores and you might run on a system that has 1 core or 2 cores, or has gobs of memory and then doesn't have gobs of memory. So you need, some of these things need to be updated. The JVM automatically takes care of a bunch of these things, but it's with the Crack API in particular, it's kind of easy for applications to get caught by something that got built in at the, like a time, for example. You know, how long did it take to start the application framework? If I did all of it on the build system, obviously it's not going to reflect the time that it took to restore the process in the in the restored process, right? I've already printed out how long it took. In fact, we saw that in the workshop, right? That 2.506 seconds message doesn't change because I've already started up the JDK, I've already started up the server in my build environment. And then when I restored, which only took a couple hundred milliseconds, that number is nowhere to be seen. I had to measure that myself. So there are some things that you might need to do to add hooks, and the Crack API provides a whole bunch of mechanisms for doing that, which unfortunately I don't have time to go into here. But there's lots of articles out on the web on how to set resources. Basically, you get a hook on a resource. You register a hook with an interface you register an interface on a resource, and then you can get a hook that happens when a checkpoint happens, so you can do something to clean it up on the checkpoint side, and then when the process restores, you'll get called to say, and we're back, and you know, it's time to do something to fix this up in the current environment. And so all of those hooks will get run before the process starts to resuscitate on the other side. Google the resource hooks for for the Crack project, and you'll get some information on that. So in terms of impact on that on our scorecard, so obviously we need to do this checkpoint run, so that sucks. And Quarkus doesn't provide any help with this one, so it's a little bit more involved. You have to do it yourself. However, you get amazing time to first response, and I'll do it as a almost perfectly green. I don't think this one's perfectly green. Oh, it is perfectly green. Okay. It is perfectly green, and I'll say if you're including the container start time in this will be as good as native image for you, probably. Because the difference between the checkpoint restore time and native image still will probably start faster if you can generate a native image for your application. But it will be drowned out by the amount of time that it'll take to start the container, and you won't notice as much. That's why it's important to take these things into consideration, because it's kind of like that, you know, 0.1 versus 10 milliseconds if you're 100 seconds later. It doesn't help with ramp up so much, although we have been looking at ways to make that better, and the rest is kind of the same. Remote JIT compilation. So this is the Semeru. Wow, I'm behind. Sorry, Semeru Cloud Compiler, the OpenJ9 JIT server. This is just every JVM that you run has a JIT compiler in here that's independently deciding what to compile for this application. This just creates a remote JIT server, so there's a very lightweight local thing which communicates with this guy, and all of the compilation work happens here, and it just feeds this guy. So that has some great advantages. It's very easy to deploy. It ships with our JDK, the Semeru Runtimes JDK, and you just run JIT server. The same way you'd run Java, you run JIT server. It's in the bin directory. It's right there. You run JIT server, and poof, you've got a JIT server, and it starts literally like you won't be able to measure it. Well, you can measure it, but you won't be able to. You won't notice the difference if you just run it yourself. I would recommend best choice is to configure SSL for the JIT server connections unless you're running on an already encrypted network. And then there's this other option here, which I also recommend, that was recently added, which allows us to generate AOT, dynamic AOT, reusable JIT code methods at the server, so that application A can compile println, and then that can get fed to all three of these without having to recompile it, which really helps accelerate the amount of time that it takes to compile across a cluster of applications. If we add this into the mix here, it's really easy to use, as I pointed out, although you could argue deploying yet another thing and giving it resources and figuring out how to manage its life cycle is a little bit complicated, so maybe I should have put this as orange. Nonetheless, time to first response by itself, it does improve things, but it doesn't get it to the caliber of checkpoint restore. Ramp up is improved, but I wouldn't say that it's as good as native image ramp up, just because native image is kind of basically just there. And the rest of these things don't change, but one place where it has a big impact here is on peak memory use. Because you've moved the JIT compiles out of the JVM process to somewhere else, you no longer see all of those memory spikes in the JVM process itself. And yes, I had to allocate a JIT server somewhere else and give it resources, but I can actually size that independently of my JVM containers, and it makes it really easy for the JVM containers to run smoothly. Final option is native image, which I think most people are probably at least a little bit familiar with these. But the idea is you run a build step to build and optimize your program, assuming that you know all the classes that are going to get compiled. You compile them all together, you run optimization on them, and you generate an executable for each application. So application A gets an executable, application B gets an executable, and then you can throw that you can take that executable and toss it around to different machines and run it. Quarkus also simplifies the building of this. You have to add about 10 lines of code to your POM XML, and really simple XML, and then building it is just as simple as adding the -p native to your package run. However, some caveats: not all Java applications can be built into native executables, and you don't always discover that in the build step. Sometimes you discover it in the run step, which is kind of unfortunate, as it discovers that it needs to load a class that it didn't know about. So that's kind of troublesome. And also this build step, because it's often optimizing tens of thousands of classes and trying to analyze them for reachability and dead code analysis, etc., that can take a while, think minutes instead of seconds. So in my workshop, most of the builds took a minute or less for most, and most of them were like in the 15, 16 seconds kind of builds. Whereas with native image, it's more like 5 minutes. So it's a quite substantial increase in the amount of time it takes to build, and that cuts into your kind of development edit cycle if you're going to use this in your production world or in your development world. So, but the advantages are startup time and memory uses are really low, and although the performance may not be as good as the JVM with JIT, especially if you're in a sort of resource-rich environment where there's lots of resources for the JIT to be able to really pump at the code. We'll put Graal image at the bottom here. So I'll color it red just because of these long build times and the fact that it may not work, and you may not discover that even during the build step. But it does very fast times, again, consistently here, because if you include container start, you probably won't measure very much difference between these two things. In my workshop, both of these were roughly 1200 milliseconds together to get virtually all of the applications, the microservice applications that I was running. All of them started in the same amount of time with checkpoint restore as they did with native image, even though the native image one actually did start quite substantially faster. Time to ramp up is also very, very good with native image. This was by far the best ramp up, but it had a weird character to it. So I can't show this in the graph, but if you looked at the throughput curves for the applications that I was looking at, the peak performance was basically right at the beginning of the run, and then it would tail off slowly over time. It was kind of weird. It's possible it's a misconfiguration on my part, but it was something that I consistently observed in all the runs and all the applications, microservices that I was doing it for, so I just mention it as a possible thing to look for when you're doing it. And peak performance here is usually less than JVMs, but your memory use is actually quite good, generally speaking. So most of these options are kind of in the pick one category, right? You can choose to do app CDS, or you can choose to do AOT class linking, or you can choose to do native image. You can't really combine them together. On the OpenJ9 side, we actually designed all of these things to work together, even though we're not quite there yet with combining these two. At least I couldn't get them to work in my workshop, so I can't claim that they do work together just yet smoothly. But the claim is, or the way that we've built it is to get all of these things basically to work together. And the reason why we did that is because we knew none of them were going to be enough by themselves. They tackle, in some cases, different parts of the problem, right? JIT server is really good here and really good here. Checkpoint is really good here. So if you start putting these things together, you can leverage the strengths of each of the technologies that we've got and offset their weaknesses. And so in the end, what we're looking for is to achieve, something that at least doesn't have any red boxes across all of these things here, right? I don't think anybody else is as close as we are to doing that. But anyway, I'm not trying to sell you OpenJ9, even though I would love for you to use OpenJ9. But so what should you choose? You have to decide, as I said before, you have to decide for yourself what metrics matter and then how important they are, right? So if you only cared about performance, right, like so much of the world did up until maybe 5 or 10 years ago when the cloud came around, Hotspot does look like the best option, right? It does consistently provide, it's the most likely to provide the best option for a long-running transactional kind of workload. Not by much, and there'll be cases where OpenJ9 will do better, but again, you measure it, right? That's how you know what's going to be better. I can make this recommendation in general, but I don't think it's going to be true in every single case, and so you need to measure it before you take that recommendation to heart. If you care about other metrics, then it gets murkier, because as you saw, the table that I put up before there's lots of different boxes and lots of different places, and so you have to be more considerate of your preferences and decide what's important to you. Do you need to save money? Do you need high performance? Do you need time to first? Do you need response times, etc.? Be skeptical of anyone who tries to tell you the answer, because if you read lots of blog articles on the internet, they're trying to sell you an answer, basically. And I would say don't trust that. You have to do your own measurements. You have to think for yourself on what's important to you in your deployments and your applications. There is no single answer here. So in this talk, I talked about a bunch of the metrics that I think you could use and maybe should use for your decision making. Please consider those, start measuring them, and weigh the results according to what matters to you. And the future is bright here. Hotspot and OpenJ9 and Graal are continuing to innovate, continuing to push boundaries, continuing to make things better. Every single one of us wants to turn our orange boxes into yellow, into green boxes, and our red boxes into orange or green boxes. So everyone's working hard here, and we're competing with each other, and you're the ultimate benefactors of all of that. So there's cool stuff coming. I like OpenJ9, but I work on it. I'm biased. Don't trust me. Try it yourselves. And hopefully for OpenJ9, we're hoping to improve the integration with with Quarkus, so that for OpenJ9, so that some of those technologies that I mentioned are a little bit easier to deploy. Kind of like specify a nice simple property rather than having to go through the steps yourselves in your own Docker containers. The IBM team here is trying to learn more about your habits with your IDEs. Independently of this talk. Has nothing to do with the subject of this talk, but we are trying to run this little survey. We'd really appreciate it if you could take a few minutes of your time and just scan that and go through the survey for us, please. We'd love to get your answers. There's nothing scary that we're asking in there, no personal information or anything like that. We're just trying to get an idea of what people are doing when they're using their IDEs and what they're looking for. And that's it. Thank you. Danke.